This video is on the closure of a set. So first, recall a definition that we had previously, and that's the definition of limit point. So if A is a subset of a metric space X, then a point X in X is a limit point of A if every open set containing X contains some element A in A other than the point X. So here we have our point X in the set A, and if we take any open set U containing X, then there must be some point A other than X that is contained in U. That's the definition of limit point. Recall that because an open set in a metric space is a union of open balls, this is true if and only if, for all epsilon greater than 0, there is some A not equal to X, such that A is an element of the ball centered at X of radius epsilon. So that's just an equivalent definition of limit point for a metric space. Also note that it might be the case that X is not an element of A, as we see over here, or it might be the case that the limit point is an element of A, but again, in that situation, we need the criteria that there's some element of A, let's call it B this time, that's in any open neighborhood of the point, in any open set containing the point, that is not equal to the point itself. So, or for all epsilon greater than 0, if Y is a limit point of A, that means there is some point A in the intersection. There is an A in the intersection of A and the ball centered at, in this case, Y of radius epsilon, if Y is a limit point of A, where A is not equal to Y. Also, we have just some notation. So we didn't use this notation before, but the set of limit points of A is denoted A prime. And so that's A prime, the set of limit points of A. Now we've got our new definition, the closure of a set. So the closure of a set A is the union of A with the limit points of A. So it's denoted A closure, and that means that A closure is equal to the union of A with its limit points. So A closure is equal to A union A prime, A union together with its limit points. And this is, we could draw this like that. Well, there's a lot of stuff going on, but so A closure contains both A and the limit points of A. A note about notation here. Unfortunately, this is the same notation that we often use for A complement. So this is not the same as A complement. So from here on out, we will try to use this notation A with a C for A complement and A with a line over it for A closure. All right, let's look at a few examples. So we saw that in the real numbers with the usual metric, we've also already found the limit points of a number of sets. So for example, the set of limit points of the open interval 1, 2 is the entire closed interval 1, 2. Every point in the interval from 1 to 2 is a limit point, and the endpoints of that interval are also limit points of that set. And therefore, the closure of the open interval from 1 to 2 is the set together with its limit points, in this case, the closed interval from 1 to 2. We also found the limit points of the set 1 over n, such that n is a natural number. So the limit points of this set, and again that's being denoted with this prime, the limit points of that set, the only limit point of that set we saw previously is the number 0. That's the only limit point. And so that means that the closure of this set, the set together with its limit points, is the original set unioned its limit point. This is sort of the only nice way to write that, I would say. One final example. We saw that the limit points of the rational numbers is the entire set of real numbers. Why is that? If we pick any x in the real numbers and any ball of positive radius, the ball centered at x of radius epsilon in the usual metric, then that ball will absolutely contain some y in the rationals, because between any two real numbers is a rational number, and therefore the set of limit points of the rational numbers is the entire set of real numbers. So again, it's the case that the closure of the rational numbers in the usual metric is the original set unioned with its limit points, in this case, the whole set of real numbers. All right, so here is a theorem about any subset of a metric space XD. So if A is a subset of a metric space, then first of all, A closure is a closed set, and secondly, A closure is a subset of every closed set containing A. So let's think about that. So we've got our set A over here, our set A closure, A together with its limit points. Recall by theorem 3.7 that a set is closed if and only if it contains all of its limit points. So what we want to show here, we want to show that the set A closure contains all of its limit points. So that's what we want to show. So we've got some x, and we are assuming that x is an element of A closure's limit points. So let's let x be a limit point of A closure, and also let's let epsilon be greater than 0. Then, by definition of limit point, that means that there is some element y that is in both A closure, both the original set, and in the ball centered at x of radius epsilon. So let's draw that over here. So because x is in the set of limit points of A closure for any epsilon greater than 0, epsilon, the ball centered at x of radius epsilon contains some point y, where y is in A closure, and y is in that ball, and where it's the case that y is not equal to the point x. That's the definition of limit point. Now, if y is actually an element of A, then that would tell us that x was an element of A, of the limit points of A, which is a subset of A closure, in which case we would be, again, done. And we'd be done because we wanted to show that x was in A closure, that A closure contains all of its limit points. So if that's the case, we're done. Otherwise, if that's not the case, then since, y is in A closure, y must be in either A or the limit points of A, or both. So otherwise, y is an element of the limit points of A. So now let's use the definition of y being in the limit point of A and see where we can go from there. So what we're going to do, let's just blow up a picture of this like epsilon ball right here. So we started with x. We've got some ball of radius epsilon contained around x. We saw that y was some point that was in A closure as well as being in this ball. Now we're going to think about a new distance, and let's make this new distance the distance here. So let's let epsilon 2 be the original epsilon minus the distance from x to y. So let's let epsilon 2 be epsilon minus the distance between x and y. By definition of limit point, since y is an element of A prime, since y is a limit point of A, there is some other element z in the ball centered at y of radius epsilon over 2, and in A where z is not equal to y. So there's got to be some, now here we've got this little ball of radius epsilon 2, and there's some z inside of that. So over here we've got our same little picture, like that, and there's some z that is in both A and in, so here's our point z. That point z must be in A and in this new ball of radius epsilon 2. Well, now that point z is also in our original ball of radius epsilon centered at x, because our second ball is inside of the first ball. So in other words, since the ball centered at y of radius epsilon sub 2 is contained in the ball centered at x of radius epsilon, that means that z is an element of the ball centered at x of radius epsilon, and z is in A. So now, if it's the case that z happens to be equal to x, we don't necessarily know that that's not true, then x is an element of A, which implies that x is an element of A closure as well. So the limit point of A closure is contained in A closure. If z is not equal to x, then by definition, x is a limit point of A, because our definition of limit point for any epsilon greater than 0, the ball centered at x of radius epsilon contains some point of A other than x itself. So then x would be in A, in the limit points of A, which would also tell us that x is in A closure. So in either case, we have shown that therefore A closure contains its limit points, and that tells us that A closure is a closed set. Our second part of this theorem is that A closure is a subset of every closed set containing A. So if we've got our set A, and we've got some closed set containing A, so let's call it F. Let's say that F is closed and A is contained in F, then it must be the case that A closure is a subset of F. It must be the case that A closure is a subset of F, where F is closed and F contains A. So that's what we're saying is true. And so you in the homework, you are going to prove the following. You're going to prove that if A is contained in F, if any set A is contained in the set F, then A closure is contained in F closure. So that's going to be a homework problem. And basically that makes this part 2 of the theorem immediate. So suppose that F is closed and A is a subset of F. Now, an equivalent definition of F being closed, or we've proved that it is equivalent for F to contain all of its limit points. So since F is closed, that means that F contains its limit points, that every limit point of F is contained in F. And so F closure, what is that equal to? F closure, by definition, is F unioned with its limit points. But this is F unioned with a subset of itself in this case. That's simply equal to F. And therefore, A closure is contained in F closure by the homework, and that is equal to the set F. So we've shown that A closure is a subset of every closed set containing A. Okay, one more theorem about the closure of a set and the interior of a set. So let A be a subset of a metric space XD. Then that set A is open if and only if A is equal to the interior of A. Part 2, the set A is closed if and only if A is equal to A closure. So again, this also is going to be homework. And both of these are what I would call definition pushing proofs. So these are both both going to be obviously bidirectional. We have to show both directions. But for the most part, each of these pieces is going to be thinking about, okay, what does it mean to be an open set? What does it mean to be a closed set? What are the definitions? And in fact, for part of the second piece is related to what we just did above, thinking about the closure of a set. So that is a homework problem, but these are really useful ideas to know, that A is an open set if and only if A is equal to the interior of A. A is a closed set if and only if A is equal to a closure.